Okay, we're going to wrap up 2.6 logarithmic functions in Barnett by looking at the properties of logs, solving some equations, and doing some applications. So why don't we take a look at that? So using the definition of a logarithm, we could solve equations that involve logs. For example, the first one here, log base b of 1,000 equals to 3. What is this really telling us? We'll convert into exponential notation. Remember, a log means find me the power, find me the exponent. So this really means b to the power of 3, right? We have the exponent here, equals to 1,000. So what number raised to the power of 3 will give you 1,000? Well, recall that 1,000 happens to be 10 cubed, so b must be 10. Okay, so that's one way to approach this equation. Sometimes you'll know the base, like in the second example, and you'll be looking for what happens when you raise the base to a certain power. So if we say log base 6 of x is equal to 5, we know the base, we know the power, so translating this into exponential language, so to speak, I will get 6 to the power of 5 is equal to x. And x must then be 7776. Okay, so in each of the above, we convert it from log to exponential form and solve the resulting equation. So that's the simple cases. Now, for more complex cases, we need to know these properties of logs. They're very nicely listed in your textbook in a nice chart. They're also available on the slides, so why don't you pause the slide for a moment here and review each one of them briefly. The most important ones that you should focus on are these three here, 5, 6, and 7. They will get used the most. Let me briefly go over these. Obviously, log base b of 1 is 0, because think about what log base b of 1 is saying. B to what power will give you 1? And well, anything raised to the 0 power except 0 is 1. Log base b of b must be 1 because b to what power, b raised to what power will give you b? The answer is 1. B to the first gives you b. Log base b of b to the x means b to what power will give me b to the x? Well, the answer better be x. Finally, b raised to the power of log base b of x equals x. Raising b to a power of a log base b, the two cancel out since they're inverses. Remember, exponential and logarithmic equations are inverses. So this just gives me x. Now on to 5. In 5 you have a product of two numbers, m and n. What you do in that case, if you have log base b of this product, you could break it up into log base b of m plus log base b of n, So that's what we've done here. In number 6 we have a quotient instead of a product. In that case, this becomes log base b of the top minus log base b of the bottom. And finally, one of the more helpful rules is rule 7. When you have log base b of some value raised to a power p, where p is a real number, you could take the p and bring it down in front and make it a multiple. So it becomes p times log base b of m, without the p being there anymore. Okay, this is a really helpful property, as you'll see in a sec. Okay, so why don't we give this a shot? Let's solve some logarithmic equations using these properties that we just went over. So notice, we have log base 4 of x plus 6 plus log base 4 of x minus 6 equals to 3. When we have multiple logs, the first step is to always put them together into a single log. From the properties that we just saw, it seems that we have log with the same base b of something plus log with the same base b of something else. The base b that I'm referring to happens to be 4 in this case. So this is log base 4 of x plus 6 times x minus 6. We can combine these into a product. I'm using that property number 5 backwards, right? Log base b of something plus log base b of something else, that could be written as log base b of the product of those two somethings. Okay, those two somethings happen to be x plus 6 and x minus 6. Okay, that equals to 3. Now from here, hopefully you remember that this is a difference of squares, right? So really you could rewrite this as log base 4 of x squared minus 36 equals to 3. Could simplify a little bit. And now we could just change this to exponential form. 4 raised to the power of 3 will give me x squared minus 36. Okay. Now this is just a quadratic equation that you guys probably remember how to solve. Let's do it anyway. 4 raised to the power of 3 is 64. So I have 64 equals x squared minus 36 add 36 to both sides and you get 100 equals x squared. So x must be equal to 10. Okay, and here is on the next slide the solution step by step. Now, one thing I want to point out, once again, right, we rewrote everything here. Notice when we have 100 equals x squared, they write the answer is plus or minus 10 at the end. But then they say x can be positive 10 only. Why is that? Let's stop for a moment and think about why that is. Okay, did you catch it? Are you thinking of it? Notice if you take x to be negative 10, then in either one of those first two expressions we started with, let's take the first one for example, replace 10 with negative 10 with x, then you would get the log of a negative number. And what's the problem with this? Well, remember, this just means find me the exponent, right? So in other words, this just means 4 to what power will give me negative 4? And the answer is none. When you take the number 4 and raise it to a power, the power is just telling you multiply 4 by itself x many times. Even if the power itself is negative, it means take this, make it into 1 over 4 to the positive power of x, right? So again, you're multiplying 4 by itself x many times. No matter how many times you multiply 4 by itself, you're never going to get negative 4 here. So this is impossible. Remember, we said that the range of this needs to be only the positive real numbers, right? The range of the log function here. So with that in mind, so that's why the answer would be x equals to 10. You would have to check when you solve these equations with both of your logs in the original equation to see what's going on. Okay, why don't we see one more application of this here in the next example, and this should be a minus. So we have log of pi minus log of 10,000 pi equals to x. Okay, and as you'll see in a little bit, every time you see log without a base, that just means log base 10. In mathematics, we usually do not write the 10 because it's understood that this is log base 10. Okay, so again, use the properties of logs here to combine the two logs on the left-hand side into a single log. And here's what it would look like. If you had a log of pi minus log of 10,000 pi, we could use the quotient rule to combine those into log of pi over 10,000 pi. Okay, equals to x. You have log base 10 of something minus log base 10 of something else. Combine those into log base 10 of the two somethings as a quotient in this case because of the difference. Okay, well from here we could cancel out a pi, simplify, and we're left with 1 over 10,000 equals to x. But 1 over 10,000 we could rewrite as 10 to the negative 4. So we have log base 10 of 10 to the negative 4 is equal to x. By the properties of logs, you could even think of it as taking this negative 4 and bringing it down. Right? Negative 4 times log base 10 of 10 equals to x. But log base 10 of 10 is just 1. So really this is negative 4 equals to x. So that's my solution. Negative 4 is equal to x. Notice in this case it's okay to have a negative number because the negative 4 is the power, right, when you combine these logs. In other words, it's just the real number in my equation. It is not involved with the logs. So that's why this is okay. Alright, so once again, this is called the common log. You will see it over and over. Log of x means the same as log base 10 of x. If no base is indicated, the logarithm is always assumed to be base 10. We also have what's called a natural log. It's denoted with ln of x. That just means log base e. So when the base is the number e, we just write ln of x instead. Okay, let's do one more example here of solving an equation. It says solve for x, obtain the exact solution of this equation in terms of e, and the equation is ln of x plus 1 minus ln of x equals to 1. So here's the solution. Okay, notice this should be x plus 1 here, right, because we had x plus 1. So we get ln of x plus 1 over x is equal to 1. Now what we're going to do next is exponentiate both sides. Okay, exponentiate both sides. What that sort of means is do e of on both sides. And then on the right hand side we get e to the first power, which is just e. And on the left hand side the e and the ln will cancel out and you're left with x plus 1 over x. Okay, so we get e is equal to x plus 1 over x. Now multiply both sides by x, and this should be e times x equals x plus 1. The x's cancel when you multiply on both sides here. This should also be e times x. My apologies there. we're moving the x on the left side, so we're collecting x terms on the left side, keeping the constants on the right. Then factor out the common factor of x, and you're left with e minus 1, and you get the one on the right hand side. Divide through and you get your answer.